So our next lecture is relative motion. This covers section 1.6 in your textbook. And a good situation that describes relative motion would be that of a person in an airplane. And if you've flown in an airplane before, you might have noticed that when you look outside the window of an airplane, it appears as if the clouds are moving very fast. And when you look at the motion inside the airplane, it's as if the plane itself is stationary and the clouds are just moving around it. But if you're an observer on the ground and you look at an airplane, you see the airplane moving with respect to the ground. But the clouds themselves, you see them moving as well. They'll be moving with respect to the wind. So the wind is independent of the movement of the airplane. The movement of the clouds is independent of the movement of the airplane. That would be your perspective as an observer on the ground. Now this is an example of relative motion. The passengers in the airplane are in one frame of reference, and you being an observer on the ground are in another frame of reference. Now when we find the velocity of an object relative to a specific frame of reference, that's called the relative velocity. You'll find that for some problems that involve multiple types of motion in different frames of references, that determining the relative velocity often simplifies solving these types of problems. Now, I'd like you to copy down the definition of relative velocity. You may want to pause in order to do that now. So to analyze relative velocity in more than one frame of reference, we use the symbol for relative velocity with two subscripts in capital letters. So what you see here is an example of showing the velocity of a canoe relative to water. So we show V with an arrow above to recognize that this is the velocity vector. And we write C, which is canoe, and then we write W, which is water. This is read as the velocity of a canoe relative to the water. So here's another example. This one involves a plane moving relative to the Earth, and the plane moving relative to the air, and the air moving relative to the Earth. So here we have an airplane. It's traveling at 490 kilometers per hour west relative to the Earth's frame of reference. So it's VPE, which is its velocity of the plane relative to the Earth, is 490 kilometers per hour west. So let's look at the wind. The wind is moving with respect to the Earth as well. Here we're going to label the wind as A, or air as A, and the plane is labeled as P. So VPA is the velocity of the plane relative to the air, and that is also sometimes called the airspeed of an airplane. And then lastly, we have the velocity of the air relative to the Earth, and that would be VAE. So velocity of A, which is the air, relative to E, which is the Earth. And we call that wind speed. And going back to the velocity of the plane, the VPE, that's sometimes called the ground speed as well. These are terms that are used when talking about relative velocities of any object that's traveling with respect to the Earth while it's also experiencing wind as well. So the equation VPE equals VPA plus VAE, in the situation that we had above, we know that the plane is moving at 430 kilometers per hour east, and the air's velocity relative to the ground is 90 kilometers per hour east. So if we want to find out what the plane's ground speed is, we add the air speed plus the wind speed. So 430 plus 90 gives us 520 kilometers per hour east. Now what you may have noticed in terms of how those variables work, or those subscripts work in the variables, that when we add a variable or a relative velocity variable to another relative velocity variable, if the last subscript is added to another relative velocity vector, and the first subscript is equal to the last subscript of the other, then our resultant becomes the relative velocity of the outside terms. So this example, if you look at this picture here, we have VPE equals VPA plus VAE. The A is on the inside, and when we add VPA plus VAE, what essentially happens is that A gets covered by the calculation between VPE. So our VPE is a sum of VPA plus VAE. This works with any relative velocity. So here's some random letters here. We have VDG. That would be equal to VDE plus VEF plus VFG. So the E is on the inside, the F is on the inside. Our resultant velocity vector becomes VDG, which is the two outside terms. Here's a sample of a problem you might get when you're solving a relative velocity assignment. So here we have a cruise ship. It's moving with a velocity of 2.8 meters per second forward relative to the water. And we have some tourists that are walking on the deck with a velocity of 1.1 meters per second relative to the deck. So we're asked to determine the velocity of the tourists relative to the water. And we're asked to do that when they are walking toward the bow of the ship. The bow is the front of the ship. So our velocity of the tourists relative to the water can be found by finding the sum of the velocity of the tourists relative to the ship plus the velocity of the ship relative to the water. Our VTS is 1.1 meters per second forward because they're walking toward the front of the ship. The ship is also moving in the forward direction, so that's 2.8 meters per second forward. So 1.1 plus 2.8 gets us to 3.9 meters per second forward. This is the velocity of the tourists relative to the water. So while they're walking 1.1 meters per second on the ship, they're also moving with the ship at 2.8 meters per second. So their total velocity is 3.8 meters per second forward. So let's say those tourists are now walking to the stern of the ship. So this would be, it would be the same calculation. It would be VTW equals VTS plus VSW. But in this case, our velocity of the tourists is now going to be a negative 1.1. So they're going back because they're going backwards. So it's 2.8 forward plus negative 1.1 forward. So when we subtract those two, we get 1.7 meters per second forward. Now it gets a bit more complicated if they're moving to the right side of the ship, or starboard. In this case, we now have a vector sum, and that's 2.8 meters per second forward plus 1.1 meters per second to the right. And I'm just going to take a quick cut of this video, and we'll switch to the paper, and I'll show you how to solve this part of the problem. So for this problem, the formula we know is VTW equals VTS plus VSW. This is a relative motion problem. The VTW is the velocity of the tourists relative to the water. The VTS is the velocity of the tourists relative to the ship. And VSW is the velocity of the ship relative to the water. So to fill this in, we would replace VTS with 1.1 to the right, that's the starboard direction, plus our VSW, which is 2.8, and that would be forward. Now to calculate this is a vector addition problem. So what we would do is we would be finding, I'll write it down here actually, the square root of 1.1 squared plus 2.8 squared. So in our calculator, we square 1.1, we square 2.8, and then we find the square root of that, we're left with 3.008. I'll just leave some extra digits. This is our magnitude. However, we need to find the direction as well. So to find the direction, which is the angle, we find the inverse tan of the lesser of these values divided by the greater of the values. This will always give us an angle that is less than 45 degrees, and that is the convention that I like to use for these types of problems. So 1.1 divided by 2.8 gives us this decimal equivalent. If we find the inverse tan of that, we're left with 21.45 degrees. Now using this, we can write our final solution here, and I will round to 2 significant digits, so 3.0 meters per second. My primary direction I would go is front. I would make a turn of 21 degrees, and that would be directed towards the right. I can box my solution, and that's how we would solve problem C. So here's another problem. We have a canoeist who can travel at 4.5 meters per second in still water, and they're crossing a river that's flowing with a velocity of 3.2 meters per second to the east. The river is 220 meters wide. So if the canoe is aimed northward, what is the velocity of the canoe relative to the shore? For this canoeist problem, we know that the formula again is going to be VCS equals VCW plus VWS, and the VCW, the velocity of the canoe relative to the water, is going to be 4.5, and that's towards the north. The velocity of the water relative to the shore is VWS, and that's going to be 3.2. And we can go straight into solving this using our vector addition. So 4.5 squared plus 3.2 squared. Let me do this on the side here. 4.5 times 4.5 plus 3.2 times 3.2. And the square root of that works out to 5.522. I have to do a side calculation, so I can do that underneath here. The inverse tangent of my lower value, 3.2, divided by my higher value, 4.5. 3.2 divided by 4.5 gets me to 35.42 degrees. And I can just round this. I end up with 5.5 meters per second. The first direction I write is the greater magnitude direction, so that would be north. The angle is 35, and then the other direction, east. And then I box my solution here. Another part of this question, it says, how long does it take the canoe to cross the river? So to solve this, we know the resultant of the two vectors, but because we're only looking at how long it takes to cross the river, and the river is has a distance that is in this north-south direction, we're really only interested in the VCW, the 4.5 north. So to solve this, I'll just do it on the side here, we know that our velocity is going to be 4.5 meters per second, right? That's going to be north. The distance to travel is 220 meters. So we can simply just do V equals D over T, rearrange that to T equals D over V. And we can solve for t, which is 220 over 4.5. And our time works out to 220 over 4.5. Works out to 48.8, and I'll just round to 9, which we can just simplify to t equals 49 seconds. How far downstream does the canoe land is the next question. So to find out how far downstream the canoe lands, we now know the time it took. We can go back using this equation, v equals d over t, and I can write that as d equals vt. This will tell us the distance, how far it lands downstream. I replace the v with my 3.2 meters per second to the east. My time is 49, but I really should be using my value here, 48.8 repeated, or 220 for 4.5. So I'm going to write this in as 48.89. That'll give me enough decimal points to make this accurate. And I've actually saved it on my calculator here. So what I'll do is I'll use that more exact value, multiply it by 3.2, and I'm left with 156.4. I need to round to my significant digits, which is 2. So that gives me 160 meters to the east. And like I said about significant digits earlier, I won't be docking marks for significant digits on in this first unit, but just start getting used to those significant digit rules because you'll need to know them later on in the course. So one last question I'll show you here. It says an airplane flies due north over Sudbury with a velocity relative to the air of 235 kilometers per hour and with a wind velocity of 65 kilometers per hour northeast. Calculate the speed and the direction of the airplane. Now for this problem, we have this airplane and we really were looking for the velocity of the plane relative to the Earth because they're asking us to find both the speed and direction. So we can do that by finding that value, VPE. VPE is equal to VPA plus VAE. That is, VPA is the velocity of the plane relative to the air, and the velocity of the air relative to the Earth. So in this case, VPE is going to equal, first we'll write our VPA, that's the plane relative to the air. We're given an air, we're given this velocity as 235 kilometers per hour. I'm not going to write the kilometers per hour part, but I will write the direction. This is directed towards the north. And the VAE is 65.0, and this is directed towards the northeast. So if it's directed towards the northeast, that means there is an angle of 45 degrees, and we can break this into components by finding the cosine of that angle and the sine of that angle, but because it's the same, it'll be the same value. So I'll do that now. 235 to the north. So usually, right, the x component would be cosine of 45 degrees. That's going to be our east direction, and our sine gives us our vertical, which would be our north direction here. These two values will end up being the same. We don't need to calculate them now, but what I do want to do is just collect the north terms. So I'm going to write this as 235 plus 65.0 sine of 45 degrees north plus 65.0 cos of 45 degrees east. So those are my two cardinal directions. This is my y component, this is my x component, and we know that this is going to be greater than that because they're essentially the same value, but this one is added to has 235 added to it. So to make this easier, I will evaluate these. So let's do, on my calculator here, 235 plus 65.0 times sine of 45. I end up with 280.96. That is towards the north. And if I just do 65 times 45, I'll do cosine, but really cosine and sine would be the same here. I'm left with 45.96 to the east. I now have to find out my vector addition from this. So 280.96 squared plus 45.96 squared. So 45.96 squared plus 280.96 times 280.96 gets us to this value. Find the square root of that, and we're left with a value of 284.69. And on the side here, I'm going to find the inverse tangent of my lesser value, 45.96, divided by my greater value, 280.96. 45.96 divided by 280.96. Find the inverse tangent of that, and I have a value of 9. That's a weird looking there. We go. Fix that. 9.29. And then I can go back here and report my answer round to 3 decimal places, or sorry, 3 significant digits. 285 kilometers per hour. I'm going towards the north direction because the north has the greater value here. And then I make a turn toward the east at an angle of 9.3 degrees. And then I can box that. That is my solution for this problem.